Hey, geometry. Definitions and properties of volume. Today's going to be one of those sort of obscure lessons again, but it's okay. Like, we'll go through it, and I'll highlight the takeaways that I want you to get at the end, and it's going to be awesome. But it's sort of a difficult way to explain the lesson. This is not in your, the student textbook, but it's in mine, and it does a little bit of review regarding the properties that we've talked about in class, so I just wanted to go through it again. So regarding property 1, we assign a numerical value greater than or equal to 0 that quantifies the size but not the shape of an object in 3 dimensions. So value greater than or equal to 0 because it has to have a size, it has to have a number value to have a size. If it was 0, it would be non-existent, correct? And that quantifies the size. So if you're comparing two different shapes and one has a larger volume number than the other, that means that it's larger. It's quantifying it. It's putting a number to it. Regarding property 2, don't worry about the properties. Just we're talking through the words. But the numbers of the properties, don't worry about it. Just as we declared that the area of a rectangle is given by the formula length by width, we are making a statement saying that the volume of a box or a right rectangular prism or a triangular prism is the area of the base times the height. That you might want to jot down, area of the base times the height. Regarding property 3, in 2 dimensions, we identify 2 figures as congruent. That means equal. If a sequence of rigid motions maps one figure onto the other so that the 2 figures coincide. We know that. We've learned that. We're good. We make the same generalization for 3 dimensions. 2 solids, such as 2 cones or 2 rectangular prisms, etc., are congruent if there is a series of 3-dimensional rigid motions that will map one onto the other. Check. We know that. Regarding property 4, the volume of a composite figure, that means a figure that is a bunch of pieces put together, is the sum of the volumes of the individual figures. You can cut a larger figure into smaller figures that you can actually measure, minus the volume where they overlap. We did this with area a few lessons ago. The area of a composite figure was the sum of the areas minus where they overlap. Regarding property 5, when a figure is formed by carving out some portion, we can find the volume of the remaining portion by subtraction. So if you had a 3-dimensional figure, and you carved something out, like you took an ice cream scoop and carved out a half of a sphere or something, you could, that's an awful shape, that's so funny, you could find the volume of this cube and subtract half a sphere, and that would give you the volume of the shape that you see. Regarding property 6, just as in lesson 1, we use upper and lower approximations comprised of rectangles and triangles to get close to the actual area of a figure. We do the same for volume of curved or irregular general right cylinders, but with the use of triangular and rectangular prisms. This is going to be the sort of crazy part of the lesson, that whole approximation thing, okay? So let's get into this. We've got all the properties that we just talked about with words. Now we have pictures. Okay, area and how it relates to volume. I'll read it. I think that's the best thing to do. So the area property is the area of a set in 2 dimensions is a number greater than or equal to 0, because if it were 0, it wouldn't have anything. It wouldn't be there, right? So it has to be greater than 0. Measures the size and set, not the shape. So area doesn't give you the shape, but it gives you sort of the quantity of what's there as far as 2 dimensions go. Volume just gives you a 3rd dimension. Yeah, it gives you a 3rd dimension, and it measures the size of what's there, but not the shape. The area of a rectangular, length and width. The right rectangular triangular prism is area of the base times height. Let's highlight that, because that's important and we need to continue to remember it. Sorry, So volume given by the area of the base times the height. A right prism is the union of finitely many overlapping right rectangular or triangular prisms. And it's the sum of the volumes of the prisms. All right, aside from that, for this shape right here, we would find the area of the base, and then multiply it times the height. And that would give us our volume. Keep on moving. Congruent regions have the same area. Congruent solids have the same volume. Check. The area of the union of two regions is the sum of the areas minus where they overlap. So we would do A plus B, and we've counted this twice, so we'd have to subtract one of them, or our area wouldn't be exact. Same with volume. We got volume of this plus the volume of this. Take away the volume where they overlap because you have included it twice, and that's not acceptable. Too much volume. The area of the difference of two regions where one is contained in the other is the difference of the areas. Okay, so we've got, we've got the area of B, which includes the area of A, so take away the area of A and you just have the area of the shaded. Same with volume. Volume of the shaded, which includes the empty one, so you take away A and you've got just the shaded part. The area A of a region can be estimated using rectangles and triangles, and that does a good job estimating. So the area is somewhere between the outside and the inside. And you can do the same thing with volume. I can put triangular and rectangular prisms inside of this and estimate the volume. Okay, we're going to actually calculate the volume. We're not going to estimate it today, but you'll see how these two are related to each other. Awesome. Let's try our opening exercise. Okay, this one says, use the following image to reason why the area of a right triangle is 1/2 base times height. Well, if I did the area of the rectangle, I would have base times height, and I have two triangles equals one rectangle. Can't spell. So if I did one triangle, I could actually divide this by 2, So I have one triangle equals 1/2 a rectangle. That is why area of a triangle is 1/2 base times height. I'm sure you guys knew that though. Guess we can do that with volume too, right? The volume is 1/2 base times height of the base times height of the three-dimensional shape. So this right here is half a rectangle. This would be volume of the triangular shape. Get that straight. Okay, volume of our triangular shape is 1/2 base times height, which is half of a rectangle times the height of your figure. If we did volume of the rectangular shape, it's just base times height, which is area of the rectangle times height of the three-dimensional shape. Okay, it's the same as the two-dimensional shape, you just multiply it by the three-dimension height of the figure. Okay, this is the area of the base times height of the figure gives you the volume. Volume equals area of the base times height of your figure. Same for if we just were doing the triangular shape here, just what's in yellow, we would have area of the base, which is 1/2 base times height, and volume equals area of the base times height of your figure, the three-dimensional height. All right, complete exercises 1 and 2, and then have a partner check your work. We'll have to trust you on this one, unless you're watching the video with a friend. So, divide the following polygonal region into triangles. Assign base and height values of your choice to each triangle, and determine the area for the entire polygon. This is what we had in the book, so I went ahead and copied it here just to help us out, because we're just assigning random values, okay? That's what it asks you to do. Assign base and height values of your choice to each triangle. So what we see here is I've got 1 triangle, 2 triangles, 3 triangles. Okay, there's 1, there's 2, and there is 3. So what we have here is a base of 12 and a height of 5. So let's do that. Triangle would be 1/2 base times height. 6 times 5 is 30. And then we'll do the red triangle. Here I have a height of, they guessed, I've got a base of 20 and a height of 9. So for this triangle, I'm going to say that the area is 1/2 base times height. 10 times 9 is 90. And then this last triangle, I need a height 11 and 22. So the area of this one's going to be 1/2 base times height. 11 times 11 is 121. Cool. So the area for the entire region would be 30 plus 90 is 120 plus 121 is 241 units squared. Awesome. Hey, we have volume now. So I'm doing a height of 10. So if you remember, I had 3 triangles and 3 areas. This triangle's area was 30. I'm going to multiply that by my height and get a volume of 300. This triangle's volume, oh, what was it? Oh, stink. 90. I had to look it up. 90 with a height of 10 gives me 900, and this last one had a volume of 11 times 11 times 10. Whoo, doggy. So my total volume would be those added together. 9, 10, 11, 12, 13, 14, 4,000, I'm off, 2,000, oh for goodness sakes. Units cubed. Very cool. Okay, let's use what we know about volume and mess with it in a different way. It's sort of like our math class just meshed with our science class, right? So problem number 3 talks about a square metal plate and a density of 10.2 grams per centimeter cubed and a weight of 2.193 kilograms. So here we see that our formula for density equals mass over volume. So we are given density and we're given mass. If you notice, our density is in grams and our mass is in kilograms. So let's go ahead and change that. So to change kilograms to grams, I need to multiply by 1,000. That gives us 2,193 grams. So density 10.2 grams per centimeter cubed equals mass grams over volume. I'm going to multiply both sides by V, which cancels it out there, and then divide both sides by 10.2 grams per centimeter cubed. if we see here, that all cancels out. I'm left with volume on the left, and my grams cancel out. This moves to the numerator, and I need a calculator. My volume is 215 centimeters cubed. Units are always cubed in volume, squared in area. Awesome. So, if the base of this plate has an area of 25 centimeters squared, determine its thickness. A square metal plate, so that's our base, but we have a height to it too. So we're really trying to figure out the thickness or the height, and we know the area of the plate is 25 centimeters squared. Volume equals area of the base times height. We know the volume, 215 centimeters cubed. Area is 25 centimeters squared times height. So if we divide, cancel those out, 215 divided by 25 is 8.6. I have 1 centimeter left, so we only actually canceled out, sorry. Centimeter squared on the bottom, and 2 of them on the top. We're left with a centimeter. Equals H. Awesome, we got it. So we got volume, and then we went ahead and finished that problem for our volume to get our height, 8.6 centimeters high. Right, a metal cup full of water has a mass of, has a mass of 1,000 grams. The cup itself, this is the mass of the water, the cup itself has a mass of 214.6 grams. If the cup has both a diameter and a height of 10 centimeters, what is the approximate density of the water? So this is, diameter is 10 centimeters, so my radius is 5 centimeters. My height is 10, my height is 10 centimeters. So, what is the approximate density of the water? Okay, let's look at it. So the mass of the water is the difference of the mass of the full cup and the mass of the empty cup. So I've got the cup has a mass of 214, and really, I mean, if I could nicely draw, oh goodness, it's still blue, sorry. Thickness here, right? That's not so bad. And then the inside, I'd have blue water. Not so bad. So I just said that the mass of the water is the difference of the mass of the full cup minus the mass of the empty cup. So the mass of the water is 1,000 grams minus 214.6 grams equals 785.4 grams. Cool. The volume of the water in the cup is equal to the volume of the cylinder with the same dimensions. So the volume of the water in the cup is equal to the volume of the cylinder with the same dimensions. Okay, that's that in there, right? Okay, I need a new page. So my volume equals my area times the height. And the area is a circle. It's pi r squared. And I know we could probably discuss thickness of the cylinder and the radius and is it really 5? But we're just going to not do that. So my radius is 5, so my area is 25 pi. My volume is 25 pi times my height, which is 10. So I'm at 250 pi. Density equals mass over volume. The mass from the previous slide was, it's still in my calculator, 785.4 grams over volume, 250 pi. What were we measuring that in? Centimeters. Centimeters cubed. So now I'm going to divide 785.4 divided by 250 and divided by pi. 1.00000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oops, too many zeros. Oh gosh, that's not an eraser. Oh, bummer. I can't erase anymore. I only had 5 zeros in my calculator. But you know what's really cool about that? Is the density of water is actually 1. Like, that's a scientific fact. I can also say that 785.4 divided by 250 is pi. Like, it's really cool. This right here is 3.1416, which is approximately pi. So when we divide pi by pi, we get 1. That was fun. So the density of water is 1 grams per centimeter cubed. Approximate. Very fun. Okay, I actually skipped the part of the lesson where we estimated volume using rectangular prisms and triangular prisms. We're good. This is what we need to know, and that would have tripled the length of the video and not given a ton of value. So I hope you're okay with that. I will make sure your problem set mirrors what we learned in the lesson. Good work today.